So in this lecture we are going to talk about the equipotential surfaces. It is evident from its name as well that the equipotential surface should have same potential throughout the surface everywhere. So a surface is said to be an equipotential surface or equipotential if potential on that surface is same everywhere, right? So if the potential on a surface is same everywhere, then the surface will be regarded as the equipotential surface. Now let's see a couple of properties of these equipotential surfaces. We can always say that metals are always equipotential surfaces. Second, electric field is always perpendicular to equipotential surface. Electric field is always perpendicular to equipotential surface. Let's say if I say that this is an equipotential surface having same potential everywhere on this surface, then I am commenting that the electric field will always be perpendicular to this surface. Reason behind this comment is that if I say that there is some electric field or the electric field on this sphere is something like that, then this electric field will have two components. One is in this x direction and the other component of electric field will be in this y direction. So if potential is same at this point A and at this point B, then if I move from this point A to B, then this component of electric field Ey will do some work in moving from A to B. So if electric field is doing some work, then we say that potential difference is equal to minus E dot dr and integration. So if the electric field has some y component, then this quantity will not be 0, and if this quantity will not be 0, then this delta V will not be 0. Delta V is not 0 means there is some difference of potential between these 2 points A and B, which should not be there because we are talking about the equipotential surface. So if we want that potential at this point A and B have to be same, then this quantity has to be 0, and this quantity will be 0 only if Ey is 0. So this y component of electric field has to be 0. So the only electric field that can be available in this region is only this Ax. So electric field is perpendicular to this equipotential surface, right? So let's see a couple of simple examples related to these equipotential surfaces. For example, if I'm given with a spherical region of different radii, let's say the sphere is not that good. Let's say this radius is 10 centimeter, and the potential at this surface is, let's say, 60 volt. The radius of this spherical region is 20 centimeter. Potential here is 30 volt. Radius of this outermost region is 60 centimeter, and the potential at this surface is 10 volt. Now if I'm asked find electric field variation with radius, and the variation of electric field with radius, then in this case how will I solve this question? Here I see that the product of radius and potential is constant. So product of potential and radius is simply constant. I can find the value of this constant by 60 into 10 centimeters, simply 0.1 meter. So that C, constant C, becomes equal to 6. So I can say that always the product of potential and radius is 6. So potential will be 6 by R. Now we know that electric field is simply minus dV by dr. Then here in this case the electric field will be minus 6 constant, differentiation of 1 by r is minus 1 by r square. So electric field as a function of radius r will be plus 6 by r square, like this only. So this is the answer for the variation of electric field with distance. Let's see one more example. If I am given this is the x-axis and this one is the y-axis, and let's say if somebody says that these are some equipotential surfaces, this is not so good. These are some equipotential surfaces. This one is the third one. So this is the equipotential surface of 10 volt. Let's say this is 20 volt. Let's say this is 30 volt. And if I'm given that this is at a distance 10 centimeter, this point effectively is at 20 centimeter, and obviously this is at some, let's say, 30 centimeter distance. So if somebody asks me find electric field in vector form, then what I'll do is I can simply say that electric field is always perpendicular to the equipotential surfaces. So if electric field is perpendicular to these equipotential surfaces, then electric field should be something like this. अब electric field can be now in this downward direction or it can be in this upward direction. So we know that electric field, in the direction of electric field, potential decreases. In the direction of electric field, potential always decreases. So potential is decreasing in this direction while moving in this direction. So electric field is in the direction of potential fall. So this is the direction of potential fall. So this will be the direction of electric field, right? In question itself, these angles are given to be 30 degrees, right? So if this is the direction of electric field, and now I have to find the value of this electric field and the direction, that is in vector form I have to find this electric field. Then what I'll do is I'll simply create electric field like this. Now we know that delta V is equal to minus E dot dr integration, right? So this E dot dr integration stands for E dot whatever is dr, let's say delta r, and cos theta. This cos theta is the angle between the delta r and electric field E. So electric field E is in this direction, and delta r, if I am taking delta r as this is delta r, let's say. So this is delta r. If this is delta r, then the angle between this delta r and electric field is simply 30 degree, and this delta r is 10 centimeter, right? This is 10 centimeter obviously. So minus E into 10 centimeter, that is 0.1 meter, 0.1 meter, into cos 30, which is root 3 by 2, is equal to delta V. Delta V is simply 10 volt. So electric field, the value of electric field comes out to be equal to 10 into 2 by root 3 by 0.1. So this electric field is, minus sign is simply telling the direction, so 200 by root 3. So this is the value of electric field. I'm taking mod of electric field so that you do not get confused with this minus sign. So electric field is 200 by root 3 in value. Now I have to, if I have found the magnitude of this electric field, then what I need more is simply the direction of this electric field. So what I do here is I'll simply take this electric field, this angle is 30 degree. I'll simply take electric field to be of magnitude 1, and I take component of this 1 in this direction. This is 1 cos 30 degree I cap, and this is simply in downward direction, this is 1 sin 30 degree minus j cap. I'll put this the unit vector. Okay, so electric field unit vector is cos 30 I cap minus sin 30 j cap. So root 3 by 2 I minus 1 by 2 j. I put this unit vector with this electric field, then I get the final result, which is E vector is equal to 200 by root 3 into root 3 by 2 I minus 1 by 2 j. So this is the final result for the calculation of electric field. Okay.